Pitt PANthers take on All Clad, no pun intended. We are Dan Abraham, Bree Bargel, Joe Friend, and Laura Rubino.
Our senior design project involved working with All Clad metal crafters. Before delving into what our project entailed, we would just like to give a brief history about the company. John Ullum founded the company in 1967 when he found that a combination of different metals provided a composite of superior results. All Clad Metals was born in 1971, following purchase by Sam Michaels in 1988. In 2004, Group SEB purchased Allclad in the hopes of expanding the company. Throughout its history, Allclad has provided quality cookware for professional chefs and home cooks.
In recent months, Allclad has begun using new equipment as a part of the lathing process, which increases precision but also increases the time necessary for completion. Using this new process on current materials is preventing several height and diameter engineering specifications to be consistently attainable. The process currently being used to create the problematic products will be reviewed to determine if the problem parts are within engineering specification. This will be done by measuring the height and diameter of the cookware using measurement tools such as height gauges and calipers. Next, we will determine whether pinch trimming prior to standard lathing process is a viable option. This process saves time during the lathing process by minimizing the size of the excess lip, which must be removed and smoothed. However, pinch trimming can only be achieved if there is enough spare material around the lip of the pot or the pan. A cost data analysis will be used to validate the benefit of the larger initial blank size to produce products with larger lips, enabling the option of pinch trimming and ensuring engineering specifications are met. Following the data analysis, standard forms will be completed to test the newly found results. These forms will include an inventory request form, special manufacturing approval, and engineering change request form.
To conduct the analysis, we needed to determine the necessary size increase for both the coils and the blanks. We were given design rules that allowed us to determine the proper size requirements from Allclad. After the size increase was determined, we ran the new blanks through the lathing process to see if any time was saved with the new process. Once we found the amount of time saved, we performed a cost analysis on the time saved versus the increased cost of material. The chart in this slide shows a comparison between the sizes of the coils and blanks currently used versus the increased size of the coils and blanks that we found. To figure out the increased material costs, we created a calculator that utilized all the factors Allclad uses for material costs. The orange boxes represent manual inputs that vary for each product. The calculator then gave us a new weight for the product and new scrap so we could determine how much money the new size would cost. The picture shown is the coils after the blank has been stamped out. That is the scrap Allclad would use to save some money.
A break-even analysis was used to determine how much time must be saved on the lathe process in order for the changes to be cost-effective. This was determined using the increase in size of the raw materials and the blanks and the weight of that size increase, in addition to the increase in savings from scrap. The necessary time saved for labor production costs to equate the original total cost can be seen in the table.
We were given around 200 large blanks that we had to cut to the proper sizes of all the different products we were testing. This involved using a circle shear to cut the blanks to different diameters and smoothing them using a sand belt provided on the floor. We ran into some roadblocks along the way with some of the parts that didn't allow us to submit engineering change requests for some of the products. We were unable to get the raw material in order to cut blanks for the 5506, so this trial run was never able to be attempted. The 5414 and 6414 do not run through the lathe, so the increase in blank cost would simply be added to the total cost with no labor time saved. Allclad would not be willing to add that nearly 10% cost increase to the raw material. The 6412 failed running through the press because the blank size was too large for that machine, so Allclad could invest in different tooling for the lathe in order to make this blank size work. On the 54046, the break-even time was about 12 seconds, and a pinch trim would never be able to save that much time. On one of the remaining 4 products, we were successfully able to get the lathe time to be less than the break-even time, resulting in the cost savings shown here. 3 of these did not save enough time on the lathe to break even or save any costs. On the 4-quart saucepan, the Pitt team helped to save Allclad over $1,000. This change will be implemented shortly. On the 2-quart and 1.5-quart saucepan, there is a cost increase annually. Quality is a huge commitment at Allclad, and because of this, the changes that we suggested will be implemented even though the cost of the blanks is increased. On the essential pan, The $160 cost increase and time saved do not actually save them any time overall, because the lathe is not the bottleneck of this process. Our final deliverable for each of the products was an engineering change request, or ECR. As you can see here, it shows the exact change in the raw material size and blank size, as well as the overall cost savings. These 4 have been submitted, and they will be approved in the next coming weeks. We had a significant amount of assistance throughout this project, and we would like to thank the following people: John Monson and Javier Orellana, who are our contacts at Clad, TJ Bloom, our project sponsor, and lastly, we'd obviously like to thank Dr. Safri for her guidance.